Okay, uh, testing software complexity classes. So will your algorithm actually finish? And there's two classes that people often talk about. So I've included that here, P and MP. P polynomial, NP non-deterministic polynomial time. So this means that NP is something that can be, some type of decision problem that can be solved in polynomial time by a non-deterministic state machine. So you remember in our design lecture, we looked at deterministic and non-deterministic state machines. And P is polynomial time for a deterministic state machine. Then we have other classes, many other classes like NP complete, NP hard, which people often talk about. So an example of algorithms in these classes, finding greatest common divisor is in P, traveling salesman is NP hard, and it can be in NP complete. Halting problem is NP hard, but not in MP. So you can see a diagram here in the center sort of that is summarizing this question. Is P equal to NP? As far as I know, we still don't know. There hasn't been any proof of this, but there is $1 million offered each year for anyone who can find a proof of this. So if you have an idea, get your money. Also, quantum computers are coming. This is really fascinating, great stuff. And we even have quantum complexity classes that will deal with stuff like integer factorization, discrete logarithm, and simulations. Okay, here's a little quiz. You've got an algorithm here. How would you describe the time complexity of this thing? So if you want to pause your video, you can. Please go ahead. Otherwise, we go on. Yeah, so looking at this thing, what's it doing? Well, you're trying to find a word in a dictionary, and the algorithm says basically open the dictionary at the halfway point and check, is your word right there, or is it in the first half of the dictionary, or is it in the second half of the dictionary? And then it recursively does that. So if you check this, actually, you'll find that there's a logarithmic relationship. So the answer will be B. And so log n will be faster. It's better time complexity than n. Okay, space complexity. This is very similar to time complexity. You just basically count stuff within your program. So we've got a C++ example here where we're either passing by value or passing by reference, if you remember that. So in this example, how much space is required if we're passing a whole array by value? Well, it will be big O of n time. So it's polynomial. Yeah, and because we're generating this thing that's the length of the array, right? What happens if instead an integer pointer to the start of the array is passed to our function? Well, then we know it's just an integer, so it'll be constant time. We have just a few integers here. That would be 1, that pointer would be there, and then we have the integer sum and I, and we're returning something. Okay, now we go on to a special case of testing software, testing recognition. So we have many different metrics for testing recognition systems. We use cross-validation usually to get some type of accuracy. We use a confusion matrix to determine where the algorithm has problems with which classes. And then for people who want to know more, there's many other measures like precision and recall. Precision measures the amount of noise that you have. Of the cases that your algorithm says are positive, how many of these are actually positive? And recall is more talking about the exhaustiveness of your algorithm. For all the cases that are ground truth positive, how many of those does your algorithm actually say are positive? Then we have F-score, which combines these two things together. It's a harmonic mean of them. Matthew's correlation coefficient is basically a very similar thing, gives similar numbers. We have ROC curves, true positive rate versus false positive rate are plotted in the ROC curve, and you have metrics like area under the curve that you can compute. There's many of these things. But I think those are pretty important ones. Confusion matrix. Okay, so here we've got an example of a confusion matrix. Why do we do this? We want to know where an algorithm fails, and a confusion matrix will summarize that in an easy way. So you plot the ground truth, what's actually this class, and the system output, what the system thinks the class is. So here we've got a system that classifies robots, robot 1, robot 2, robot 3. How would you interpret this? I'm just going to go ahead. If you want, you can pause your video. But otherwise, I'm going ahead now. So you can see that this system isn't able to classify robot 3 at all. It has really big problems with that. So basically, the recall is terrible. The precision in this case is great. I mean, because it only says 3 times that a robot is R3 and it's all correct. And what does this mean? I mean, if I saw this, I would really look at the data for R3 and try to find, especially the misclassified samples, try to find what unique properties of this class exist. If you're designing your own features, if you're not designing your own features, you might have to think in a different way. You might have to get more data for R3. You might have to check the data that it's been properly labeled. You might have to consider your classification scheme. Is there really a separate class called R3? Your sensors, are you sensing enough to distinguish between these? Okay, and we've got one more example, and this example is very similar, but a little bit different. So here, the R3 is classified perfectly by our system, but R1 and R2 are not. So here, I would look at the misclassified samples of R1 and R2. So I mean, just to say it, and like I said it before, here, we have great recall. All the positive samples of R3 are labeled as such. Great recall for R3, but bad precision. So there's false positives that are mixed in there. So we should look at R1 and R2, and we should think about sort of the same things as before. Do we have enough data for R1 and R2? Do we want to use weighting maybe? But it seems to be a little bit of a nicer result. Okay, hardware. So your focus in this course and in the master program where our students usually come from is on software mostly. So this is just a stub for now, but if you want to evaluate electronics or hardware, then you look at various similar things. You can use stress tests applying high voltage or high current and see how your system does, or heavy things or whatever, fast speeds. Okay, we go on to report. One part of evaluation also is reporting about the systems that we've evaluated. Often we report via research papers or presentations. So for research papers, we know that the criteria we look at are the novelty and the methodology. So for example, was a difficult challenge tackled? Was the methods used correct? And was it thorough? Did it solve most of the problem or just a tiny piece? Then we also look at the relevance, importance of the work, and also how it was disseminated. Also, the venue in which research is published can have an effect. So for example, if it's a journal or a conference, and the impact factor is also important. Another way to present research often is through a presentation. And here, one of the important things to convey is that people from different fields can make presentations in a different way. Engineering might not be the way that you learned if you went to some generic workshop. So it's important to also learn how to do a good engineering presentation. Here's one example of a presentation. What do you think about this? Well, I would say that I would point out a few things that are mistakes or undesirable. So basically, people often hear that using sort of a nice looking image or video and not having any text is a good way to go. But this is actually a problem for anybody who doesn't have perfect English, who doesn't have very good ears to hear what you're saying. Another problem is when people just leave slides like this with absolutely nothing to see, really, for minutes and minutes while they talk and talk and talk. It can get very boring. Another thing is when we use images that aren't really meaningful. They look sort of nice, but people don't say anything about them. And then it seems like you're not being very logical, maybe, or that you don't even have anything important to say, which isn't very good. So the important things, if you have something important to say, you should probably write it out in short text. Example 2, okay, what do we think about this one? Well, I would say overall that there's a lot of text here, so it's the reverse of the first one, but probably too much. There's not so much information there. A lot of it is just too much words. In the top part, you see introduction, methods, discussion, conclusion. We always talk about this with research. That's typical. So you're just wasting people's time if you have that in your presentation. The middle part, this is just overly wordy. It's really a long sentence when there's no reason for it. At the bottom, we have three statements, and there's no logical order. The first one and the third one are about motivation. The second one is about what you're doing, your approach. So this is a very common problem in the presentations that I often see. Example 3, what can we say about this slide? Well, I think this slide is awesome. The guy who did it is probably really amazing. I have nothing bad to say about this. Slide 4. Okay, well, this one, we have some text, we have some images, great, but it's hard to understand. So at the top, we have acronyms that aren't spelled out. We've never seen this before. We have no idea what it means. It's a very easy way to get people to fall asleep and forget about what you're saying. You can daydream about eating something. So spell out your acronyms. Second, we can't read the text on the graph. Whatever that's trying to show, the font is way too small to read. Third, the bars, the columns of this graph blend together. It's hard to see what's the difference in the colors. And this is a tricky one because we often make graphs in color, like red, blue, green. And then when people print it out in black and white, they can't tell the difference between the bars. Then there's a ton of missing information. Maybe that's the worst thing about this. So what was the goal of the experiment? What was the approach that was done to realize that goal? How many data were obtained? How many participants were there? And then we have a result, 67%, but we don't know what that means. So is that good? Is it bad? Why is it 67%? Okay, so now we can actually go to our little quiz again. And the answer is A. Student's T-test was designed for a beer company, Guinness, by a person under the pseudonym of student, because he didn't want to give his real name. C, lady tasting tea. This is actually a famous experiment which was about randomization of conditions. So there was a lady who claimed that she could tell the difference between if somebody put in milk and then tea, or tea and then milk. D, an extension of the S-test. I've never heard about S-test. T was actually, it was short for test, for hypothesis test statistic, the T statistic, and that went over to test then. Okay, we're done. Yay! So now we've done with all of these different parts of the development cycle for embedded and intelligent systems. So that was 10 parts for this online series. What have you learned? You'll also, if you're taking this course, you'll also attend various other lectures and do other labs with various teachers other than me. And at the end of this, we want to also look at the takeaway message examples in the course description. This is sort of a minimum of what you should take away from this course. So we have some questions in different areas like design, recognition. First one is, what's the difference between waterfall or agile? So we can say waterfall is sequential, agile is cyclic. High or low fidelity prototypes? You could say high fidelity prototypes give you very accurate feedback. Low fidelity is very practical. It's very fast and nice, non-costly. Software, most significant byte, least significant byte. If you have something like AAFF in hex, then your most significant byte would be AA, your least significant byte would be FF, and then we also have big endian and little endian attached to that, if you remember. So big endian often used with networks, little endian with Intel computers, where you would send in little endian, you would send the little end first. Process or a thread. So what is the memory like? Is the memory not shared in a process or shared in a thread? Kinematics or dynamics? Mass. Are you calculating stuff related to mass? Then it's dynamics, otherwise kinematics. Maybe. Kalman or particle filter. This is sort of looking at, if you remember, we talked about Kalman being a very optimal way to solve for some simpler problems where we have a good idea of how they work. So Gaussian, affected by Gaussian noise. Particle filter is a good enough solution for some complex problems which might not be, where the noise might not be Gaussian. K and N, K means, well, K nearest neighbor is supervised usually. K means is usually unsupervised. It's a clustering thing. RGB, HSV. So these are color spaces. HSV is good for color picking. RGB is a standard for additive color. And so if you have like 3 LEDs, red, green, and blue, you can create white. CAM and denim, these are communication messages. Cooperative awareness message and decentralized environmental message. This CAM, it's like a heartbeat message where a robot can talk about its position, for example. And denim, it's like if there's a traffic jam or an accident, then your robot can tell other robots about that. So it's, yeah, I don't know. You can call it heartbeat, so constant versus occasional would be one way to distinguish that. TCP and UDP, do you have a handshake for TCP? Or do you just send stuff and not really care if some things go missing or if it's not in exactly the right order? Yeah, okay, great. So, thank you for listening. That's the last lecture. Great, congratulations for completing it. Yay. See you.